Alright guys, so this is going to be section 6.1 part 2. We're going to start with the rotations. So we'll do rotations and then dilations. So the third and fourth types of transformations. This starts where we ended, so on page 230 of your notebook, or of your workbook. Okay, so the new skill we're going to work with, first of all, is working with rotations. So rotation is a transformation in which parts of an object are turned about a fixed point called the center of rotation. In order to perform the rotation, you must know the degree and the direction of the rotation. So degree is how far, how many degrees we're going to turn of that circle. The direction is going to be clockwise or counterclockwise. So clockwise is the way a clock turns. In that direction. Counterclockwise is opposite to the hands of a clock, so going backwards. Okay, so using the origin as the center of rotation, rotate the shape 90 degrees, 180 degrees, and 270 degrees clockwise. State the coordinates of the translated vertices. So when you're doing these, the coordinates or the Cartesian plane is split into 90-degree sections. So each one from here to here is 90 degrees. From here to here is 90 degrees. Each chunk is a 90-degree rotation. That means if we're changing something by 90 degrees, we're doing 1/4 turn. If we're going 180 degrees, we're going halfway around the circle. And if we're going 270 degrees, we're going 3/4 of the way around the circle. Okay, so each section of the graph is 90 degrees. The other thing you need to know is the coordinates. So the quadrants of the coordinate plane are numbered as follows. This top corner, the one we use the most often, is always quadrant 1. And then we number them counterclockwise. So it goes 1, counterclockwise to 2, 3, and 4. So 1, 2, 3 is over here, and 4. We do it backwards because the 1 and 2 are typically the most common ones we use, and then we just follow that pattern of 3, 4. Okay, the first part of this example, it actually shows you the solution on the next page. But this one said for rotate 90, 180, and 270 degrees clockwise. So what it's telling you to do is start by identifying the coordinates of the vertices in the original shape. So label them all out, write on your coordinates. Then it says a 90-degree rotation. If we're rotating clockwise with the origin, it moves from the first quadrant to the fourth quadrant. So the x-coordinates will be positive numbers and the y-coordinates will be negative. The vertices will be the same distance from the origin as in the original shape. So vertex A remains in the same location because it's at the center of the center of rotation. Vertex B, 1, 3, rotates to 3, -1. Vertex C rotates from 4, 4 to 4, -4. And D from 3, 1 to 1, -3. This shows that when a point rotates 90 degrees clockwise about the origin, the x-coordinate changes its sign, then the x-coordinate and the y-coordinate switch positions. I don't like this version. I find it hard to picture what's going to happen and how the numbers are going to change. For me, it's easier to actually think about rotating the shape. So I'm going to go down here and show you how I would do this. Okay, so this was our original right here, A, B, C, D. And if we're going to rotate 90 degrees, I need to think about moving my axis 90 degrees clockwise. So the way I think of it is this line right here. If I rotate this line 90 degrees, is going to become this reference line right here. I've turned it 90 degrees. And on my original, my shape was on this side of this line. And if I rotate that all the way down, it's going to be this side of this line. So it's like I'm taking this section and I'm turning the whole thing. So about my center of rotation, I'm turning, see if they'll let me do this. I'm turning it, maybe it won't. No, it won't let me rotate it. Okay, it's not gonna let me do it. But it's like I'm turning that whole quadrant into the second one by moving everything from here this way. So my original point A was at my center of the origin, or center of rotation, which means my A point is going to stay right there. To get to B, I had to go along my left reference line 3 spaces and then 1 away from it to get to point B. Which means in my new one, I'm going to go along my reference line 3 spaces and 1 away to get to my new B coordinate. To get to C from my original, I had to go up 1, 2, 3, 4 along my line, my reference line, and then 4 away. So in my new one, I have to go 4 along my line and 4 away, which brings me down here. And to get to D in my original, I'm always using that original reference line. I had to go up 1 and across 3, or 3 away from my line. So I'm going to go 1 along my line and down 3, or away 3, to get to my new one. So for me, it's easier to visualize turning this or referencing this rather than what the coordinates are actually going to do. I find it really difficult to figure out what the coordinates, how the coordinates are going to change. I like to just draw it. Okay, so this would be on my 90-degree rotation from my original. My 180-degree rotation would be from this original position, turning my reference line into this line right here, and facing that way. So again, I had to go, my A point stays at my origin. I had to go 1 along my reference line and out 3 to get to D. So 1 along, out 3. This would be my new D. Oh, sorry, I did that backwards. My reference line, so 1 along my reference line and out 3 is out here. To get to B, I had to go 1, 2, 3 along my reference line and 1 over. So 3 along my reference line, 1 over takes me to B. And C was 4 along the line, 4 away from the line. So 4 along the line, 4 away from the line. So this right here is my 180-degree rotation. And then the last one was the 270-degree rotation. 270 degrees counterclockwise starts there, comes all the way around to here. So my reference line is this one now. And if I could have spun everything around, everything would be up from that. So along my reference line to get to D, I had to go up 1 and 3 away. So along my line 1, 3 away takes me to point D. Point B was along my reference line by 3 and 1 away. So along my reference line by 3 and 1 away. And then to get to C, it was along my reference line 4, 4 away. So along my reference line 4 and 4 away. So this is my shape after it's been rotated 270 degrees. Okay, I like this way better. I like to think about how these things are going to turn. Okay, same thing here. It says rotate the following shapes about the origin in the direction and the degrees indicated. So we're doing 180 degrees clockwise. You can pick this as your reference line, or you can pick this as your reference line. It doesn't matter. But pick one of them. and stick with it. So this is going to be my reference line, and my shape is on this side of my line. So 180 degrees clockwise. Clockwise is always the way the clock turns. So I'm going to do 180 degrees. So halfway with this point here would be 90 degrees. 180 is all the way up to the top. And my arrow would have pointed this direction here, which means it's pointing that direction there. So my shape should end up in this coordinate somewhere, in this quadrant somewhere, sorry. To figure out where exactly it should be, I have to look in reference to my original reference line that I picked. So the original reference line I picked the y-axis. So to get to point A, I had to go down my reference line and 3 away. In my new one, my reference line is up here. So I'm going to go 1 along my reference line, 3 away. A prime is going to be over there. To get to B, it was 1 along my reference line, 1 away. So 1 along my reference line, 1 away. C was 3 along my reference line and 1 away. So 1, 2, 3 along my reference line, 1 away. D was 3, 4 along my reference line and 2 away. So 4 along my reference line, 2 away. E was 1, 2, 3 along my reference, 1, 2, 3 away. So 1, 2, 3, 1, 2, 3. Puts my E value right there. So my new shape is that guy right there. Okay, so it's like I spun that all the way around that middle reference point. If I'm doing a 90-degree clockwise, clockwise is the way the clock turns, 90 degrees is 1/4 of a turn. So my reference line I'm going to pick is this one, but again, it doesn't matter if I pick that one or the one below it. And my shape is on this side of my line, which means when I turn it, this is going to be my reference line, and my shape is going to be on that side of the line. Okay, so my reference line was here, and my shape is on that side, so my reference line's here, my shape's going to be on that side. To get to point B, I have to go 3 points along my reference line, so 3 points along my reference line puts my new B1 right there. To get to A, I go 3 along my line and 3 away. So 3 along my line, 3 away puts A right there. To get to C, I go 1 along my line and 3 away. So 1 along my line, 3 away. So my C prime is up there. That makes this my new shape. Okay, so the next little part is just asking you how would the coordinates change. So if a shape in the first quadrant is rotated 90 degrees counterclockwise about the origin, in what quadrant will the resulting image be located? How will the coordinates be affected? We're going to ignore this how will the coordinates be affected for now, because that's this general kind of change. We'll look at it with coordinates in part B. If we have a shape that's in the first quadrant, so a shape that's over here, and we rotate 90 degrees counterclockwise about the origin. 90 degrees is a quarter turn. Counterclockwise is opposite. It's going to end up over here. And our quadrants are labeled 1, 2, 3, 4. So it's going to move into quadrant 2. Okay, so that's all that's asking for. We'll look at how the coordinates actually change by doing one with a shape. So this one says rotate the shape ABC 90 degrees counterclockwise about the origin and label the vertices A prime, B prime, C prime. State their coordinates. So 90 degrees counterclockwise about the origin is opposite to the way the clock goes. So I'm going to pick this as my reference line, and my shape is below it. which means when I rotate 90 degrees counterclockwise, this becomes my shape, my reference line, and my shape's going to be on that side. So to get to B, I go 2 along my reference line and 1 away. So my new B is going to be 2 along my reference line, 1 away. To get to A, I go 1, 2, 3, 4, 5 along my line, 3 down, or 3 away. So 1, 2, 3, 4, 5 along my line, 3 away. To get to C, I'm going 1, 2, 3, 4 along my line, and 1, 2, 3, 4, 5 away from it. So 1, 2, 3, 4 along, 1, 2, 3, 4, 5 away. So that is my new shape once it's been rotated 90 degrees counterclockwise. The coordinate piece of it wants to know the x and y values at each point. So when I look at point B, my coordinates are always my x first. This is my negative x side. Down is my negative y. So I'm going 2 in my x, negative x direction, 1 in my negative y direction. For point B prime, x direction first, I have to go 1 in the positive x direction, but still down 2, so 1 and negative 2. My coordinate for 4, I have to go 1, 2, 3, 4, 5 in my negative x direction, 1, 2, 3 in my negative y. My new A, I go 3 in my positive x direction, and I go 1, 2, 3, 4, 5 in my negative y. To get to my original point C, I'm 4 in my negative x direction, 1, 2, 3, 4, 5 in my negative y. My new C value is 1, 2, 3, 4, 5 in my positive x direction, and 1, 2, 3, 4 down. So those are my new coordinates. There is actually a pattern to how my coordinates change. If I compare my B values, my original was -2, -1, and it turned into 1 and -2. So if I look at my numbers, my y value changed, or my 1 changed from a negative to a positive, and I switched my x's and my y's. So this one, -1 became +1, but then my x value became a y value. My swapping, my +1 now became a negative, or my -1 became a +1. There's a pattern to all of this. That's the same for each one of these. But seeing the pattern and knowing the pattern and memorizing that pattern, it's different for every, so if you change 90 degrees, it's a different pattern than if you change 180 or if you rotate 270. And the pattern's different if you go clockwise or counterclockwise. So it would be 4 different things times 2, so 8 different things you'd have to remember. It's not easy. The easiest way to do it, just actually draw or rotate things and find your new coordinates. Okay, part C says rotate shape ABC 270 degrees about the origin on the same coordinate plane. How does the resulting image compare to A prime, B prime, C prime, and why? So if we go back a page, it wants us to now go 270 degrees counterclockwise. Or sorry, clockwise. And if I do that, if I go 270 degrees from my original, so this was my original line, and my shape was below here, I'm going to go 90, 180, 270 degrees is going to be this line, and my shape was below, so it would be here, up, right here. All my points are going to end up in exactly the same position, because my reference line and the side of my line are still the same. So if I rotate 90 degrees one way or 270 degrees the opposite way, I'm still going to end up with the same result. And that's all this is trying to show you. Okay, it's exactly the same. And it's exactly the same because a 90-degree rotation one direction is the same as a 270-degree rotation in the opposite direction. Okay, the last piece for rotations is how to compare if something is actually a rotation or not. So it says Misha is designing the propeller for a toy helicopter. The blades need to be evenly spaced around the origin. That is, 3 of the blades must be 90, 180, and 270-degree rotations of the first blade. She's drawn the following sketch of the propeller. If blade 1 is correctly placed, which of the other 3 blades is incorrectly drawn? So this is our actual original. And what we want to find is those vertices, because those nice crossing points are the things we want to try and line up. So if I do a 90-degree rotation, and I'm going to say this is my reference line, and everything is on this side of my line. A 90-degree rotation of that is going to be to right here. So this is going to become my reference line, and everything's going to be on that side of it. So each one of these points should be still the same. So to get to this first point right here, I have to go 1, 2, 3 along my line and 1 away. So 1, 2, 3 along my line and 1 away. I'm going to call this A just so that I've got a way of keeping track of them. A and A prime. We call this one B. To get to B, I have to go 1, 2, 3, 4, 5, 6, 7 spaces along my line, and 1, 2, 3, 4, 5 away from it. So 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. My B prime should be right there. It's not, which means she's probably drawn something wrong in this blade. We can check our last point. We go 1, 2, 3, 4, 5, 6 along the line, and 1, 2, 3, 4, 5, 6 to out from the line. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. This would be C prime if we call this original C. So blade 2 isn't drawn properly. One of the points was right, but then the other 2 weren't. Because it just says which of the other 3, we should actually check all of them. The other ones look okay. Blade 2 is definitely drawn incorrectly because the points don't line up. Okay, so that's it for rotations. The next is dilations. Dilations are the only transformation that actually changes the size of our shape. Okay, so it enlarges or reduces a shape or an object. This is the only time what we draw gets bigger or smaller. In order to do a dilation, you have to know the scale factor, which is the number by which the side lengths are multiplied in order to draw the dilation. So a scale factor greater than 1 will result in an enlargement, and a scale factor of less than 1 will result in a reduction. Okay, this is good to know because it helps you know if what you've done is right. If your scale factor is bigger than 1, so 1, 2, 3, 4, 5, you should end up with a bigger shape in the end. If your scale factor is less than 1 just means a decimal number or a fraction. So we're talking like 0.5, 0.75, 0.1. Or if we've got fractions that are decimals, like 3 over 4 or 2 over 3. Whatever it is that we've got, it's a number less than 1. Don't think of less than 1 meaning negative numbers. It's not negative. We're talking about numbers between 0 and 1. Okay, the original, after we do an enlargement or after we do a dilation, the original shape and the image will be something known as similar figures. So a similar figure, the definition is off over here on the side. They're figures that are the same shape. Their corresponding angles have to be congruent or the same, and the corresponding sides must be proportional. All this is saying it's the exact same shape, it's either bigger or smaller. So all of your angles are still exactly the same size, and if one side got twice as big, then all of your sides have to get twice as big. If one side got half as big or got divided by 2, got half, then all of your sides have to do the same thing. So it says, although dilation is a commonly used term to mean making bigger, in math it's used in contexts with either enlargements or reductions. So dilation is just the term for making it bigger or smaller. Enlargement is getting bigger. Reduction is getting smaller. Okay, so this example says the rectangle below is 4 centimeters long by 2 centimeters wide. So that means each one of these squares is 1 centimeter because we've got 4 by 2. Dilate the rectangle by a scale factor of 2. What are the side lengths? So to change something by a scale factor, the new shape we make, you always take your original and you times it by the scale factor. So if I want to find my new length, I take my original length, times it by the scale factor. If I want to find my new width, I take my original width, times it by the scale factor. So in this case, I want to dilate by a scale factor of 2. So my length is going to be my original length, which was 4 centimeters, times my scale factor, which is 2. 4 times 2 is going to be 8 centimeters. My original width was 2 centimeters. I want to times it by my scale factor of 2, which is going to give me 4 centimeters. So my new shape will have the dimensions of 8 centimeters by 4 centimeters. In order to draw my new shape, I have to pick one of my vertices that isn't going to change. And so I usually pick the bottom left-hand corner. And my new one is going to be 8 centimeters long. So 8 boxes by 4 centimeters wide. So that is going to be the size of my dilation or my enlargement, my scale factor of 2. I knew it was going to get bigger because this 2 is bigger than 1. So I'm just going to use a different color for the next one. The next one says dilate the rectangle by a scale factor of 0.5. What are the side lengths? So 0.5 is the number less than 1. I should get smaller side lengths. So my original length, or my new length, is going to be my original, so 4 centimeters, times my scale factor of 0.5. 4 times 0.5 is going to be 2. To find my new width, I take my original width, which was 2 centimeters, times it by my scale factor of 0.5, which is going to be 1 centimeter. So my new one in this case is 2 centimeters long by 1 centimeter wide. So this right here, this little box, is going to be my dilation by a scale factor of 0.5 or my reduction. In each case, whether it got bigger or it got smaller, I still have right-angled corners and I still have a consistent size ratio. So for my enlargement, I made my sides bigger by a factor of 2, so times by 2 in both cases. In my reduction, I times by 0.5 in both cases. I still have similar figures. The last thing it wants you to do is calculate a scale factor. So it says the dilation of the rectangle resulted in a rectangle that was 14 centimeters wide by 7 centimeters. What scale factor was used? So this right here is a formula you need to know, that the new equals the original times the scale factor. We can rearrange that formula to solve for the scale factor as well. If we ever want to find the scale factor, it's going to be the new length, or the new side length, divided by the original side. Keeping in mind, you have to use the sides that are in the same position. So if you use the length, you have to use the length. If you use the new width, you have to use the old width. They have to match up. So this actually should say 14 centimeters long by 7 centimeters wide. Otherwise, this doesn't actually work. So part C says the dilation of the rectangle resulted in a rectangle 14 centimeters long by 7 centimeters wide. What scale factor was used? So to find the scale factor, it's always the new divided by the original. So my new length is 14. My original length, coming way back to the original question, was 4. And 14 divided by 4 is going to be 3.5. And the centimeters on top, centimeters on the bottom cancel. There are no units for scale factor. I can do the same thing for the width, although I don't actually have to unless it's asking me to check if things are a dilation. If I use my width, my new width divided by my original width is going to be, so my new is 7 centimeters. My original was 2 centimeters from way up here. 7 divided by 2 is also going to be 3.5 because the centimeters cancel. Both of my scale factors are equal. It doesn't matter if I looked at the length or the width, it gives me the same scale factor, which means these are actually dilations of one another. If I got two different scale factors, then it's not actually a similar figure to what I started with. It's not a proper dilation. So that's how you actually check if something is a dilation of something else. Okay, the rest of this, they just work through it. Same thing. So working with just the idea of dilations, says a scalene triangle has side lengths of 5.2, 6.4, and 9.6 centimeters. What will the lengths of the sides be if it undergoes a dilation by each of the following scale factors? So scale factor of 7 is bigger than 1. It should get bigger. So I take all three of my side lengths and times them by my scale factor. Because my new side lengths equals my original times my scale factor. So my originals were 5.2 centimeters, 6.4 centimeters, and 9.6 centimeters. And I'm going to times them by my scale factor. So 7 times 7 times 7. When I do this, I get 36.4 centimeters, 44.8 centimeters, and 67.2 centimeters. So those are the dimensions of my dilation or my enlarged image. For part B, my scale factor is less than 1, which means it should get smaller. Same thing though, I take my original sides and I times them by my scale factor. So times 0.4 times 0.4 times 0.4, which means my new side lengths are going to be 2.08, 2.56, and 3.84. So again, it looks like they've gotten smaller. My 5.2 started out at 5.2, turned into 2.08. The next question is talking about figuring out if pictures will fit in frames. So basically trying to figure out if we can enlarge or reduce a photo to have it fit in a frame. So it says Rob took a digital photograph that's 9 inches by 15 inches. He has one picture frame that's 5 by 8 and one that's 8 by 10. Can the photograph be dilated to fit the frames? Explain your answer. So we want to compare our original to the 5 by 8 frame, and then we want to compare our original to the 8 by 10 frame to see if the things are going to fit. So my original is 9 by 15, and I want to try and put it into a frame that is 5 by 8. And if what I want to do is calculate my scale factors for all of my matching sides, and if my scale factors match, then this picture will perfectly fit in those frames. If it doesn't match, then it's not going to fit properly. So when I compare my 9 and my 5, this is my new, this is my original. So to calculate my scale factor, it's always the new side divided by the original side. So 5 divided by 9 is going to be 0.55 repeating. Then I want to compare my other matching sides. So my scale factor is always the new divided by the original. So my new side for the width is 8 over 15, and if I do 8 over 15 in my calculator, I end up with 0.53. Repeating, scale factors are not the same, so the picture won't perfectly fit. Okay, it might actually fit in the frame, but it's not going to fill up the frame. It won't fit the same way. So the 5 by 8 frame is not going to work. We can check the 8 by 10 frame by doing the same thing. So my original is 9 by 15. We want to see if we can turn it into an 8 by 10. We're going to do the same thing. We're going to match up our matching sides. So my scale factor is going to be the new divided by the original. This is my new one, the frame. My original is the picture he actually took. So 8 divided by 9 is going to be 0.88 repeating. If I do the same thing for my other, my new over the original is going to be 10 over 15. 10 over 15 is 0.66 repeating. Also not going to work. The scale factors don't match. If you had to pick one of these frames to use, the 5 by 8 frame is going to be a closer match than the 9 by or the 8 by 10 because the scale factors are very similar for the 9 or the 5 by 8, the 0.55 and the 0.53. Whereas for the 8 by 10, we've got 0.88 and 0.66, so there'd be a lot of empty space if we tried to use that one, or we'd have to cut a lot off. But in either case, that's what we're trying to figure out. If the scale factors are exactly the same in both cases, then it's going to be an exact match. It's just going to be bigger or smaller. The second part of this says Rob wants to make a poster of the photograph by dilating it by a scale factor of 3. What will the dimensions of the poster be in feet and inches? So scale factor of 3, 3 is bigger than 1, so it should get bigger. So we've got our original. That's 9 by 15. And we want to increase it by a scale factor of 3 to get a bigger poster size. So one side, I'm going to call this the length and this the width, just so I'm clear which side I'm working with. If I want my new length, it's going to be my original length times my scale factor. So 15 times 3 is 45 inches. For my new width, I take my original width, times it by my scale factor. So this is going to be 27 inches. 9 times 3 is 27. So if it hadn't asked for specific units, you'd be done. This is my new poster. Unfortunately, it asks for your answer in feet and inches. So to turn it into feet and inches, we have to divide out however many feet we can from our answers. So 27 inches, if I divide it by 12, divided by 12 is going to be 2.25, and this number tells me my feet. 2 feet times 12 inches per foot is 24 inches. So that means from 24 to 27, I have 3 inches left over. So this is going to be 2 feet, 3 inches. So 27 inches equals 2 feet and 3 inches. I do the same thing for my 45. 45 inches divided by 12 is going to be 3.75. This is telling me my number of feet. My whole number is my number of feet. So 3 times 12 inches in a foot is 36 inches I've used up. I had 45, so I've got 3 feet. 45 minus 36 is going to be 9 inches left over. So 45 inches is 3 feet, 9 inches. When we get into the measurement unit, which was section or chapter 2 that we've skipped over so far, we're going to do more of this conversion. So don't worry too much if this conversion is not making sense right now. But we got 2 feet, 3 inches by 3 feet, 9 inches. Last example is about boxes. Emmanuelle is making 3 nesting wooden storage boxes in her woodworking shop. The mid-size box is 45 centimeters long, 30 centimeters wide, and 25 centimeters tall. The larger box is 58.5 centimeters long. If it's a dilation of the mid-size box, what scale factor was used? What are the width and height of the larger box? For word problems, it helps to draw a picture first. So we have a medium-sized box. And on that medium-sized box, I know that it's 45 centimeters long. So my length is 45 centimeters. My width is 30 centimeters. And my height is 25 centimeters. That's my medium-sized box. I want to know the dimensions of my large box. And it tells me the large box is 58.5 centimeters long. So I called the bottom side of my medium box the length. So the bottom side of my large box is also the length, which is 58.5 centimeters. First thing the question is asking me for is what scale factor was used. So this is my original. The large one is my new. Calculate scale factor. Scale factor is always the new side divided by the original side. So in this case, 58.5 divided by 45 centimeters. My centimeters are going to cancel out. And 58.5 divided by 45 is going to be 1.3. So my scale factor is equal to 1.3. It's a number bigger than 1, even though it's not very much bigger than 1, so my box is getting larger. The next part says, what are the width and the height of the larger box? Now that I know my scale factor, I can calculate those because I know that my new side is the same thing as my original times my scale factor. So for my width, my original width was 30 centimeters. I'm going to times it by my scale factor of 1.3. 30 times 1.3 is 39 centimeters. So my new width is going to be 39 centimeters. I'm going to do my height up here. My height, same thing. My new is always equal to my original times my scale factor. So my original height was 25 centimeters times my scale factor of 1.3. So my new height is going to be 32.5 centimeters. I was looking at the wrong question. So bigger than 25. So this new height is 32.5 centimeters. It's centimeters in my answer because it was centimeters in my original. Okay, so as long as it gives you a pair of side lengths that match up, like the length and the length, the width and the width, you can find your scale factor. Once you know your scale factor, you can use that scale factor to calculate the rest of your side lengths. Same kind of thing is going to happen for part B. It says the smaller box is a dilation of the mid-sized box by a scale factor of 3/4. 3/4 is less than 1, so this is going to make our box smaller. What are the dimensions of the smaller box? So it's based on our mid-sized one, our medium-sized. So we know our medium-sized box, the length was 45 centimeters, the width was 30 centimeters, and the height was 25 centimeters. We're going to make a new box, but we're going to times it by our scale factor of 3/4 to make a box that's smaller. So we need this length, we need this width, and we need this height. Because we're given the scale factor, we don't have to calculate the scale factor. All we got to do is take our originals and times it by the scale factor because the new side length equals the original side length times the scale factor. This is our original, this is our new. So for the length, our original length was 45 centimeters times our scale factor of 3/4. So in your calculator, you do 45 times 3 divided by 4. You're going to get 33.75 centimeters. For the width, our original was 30 centimeters times by our scale factor of 3/4. 30 times 3/4 is going to be 22.5 centimeters. Height is originally 25 centimeters times the scale factor of 3/4. 25 times 3/4 is 18.75 centimeters. So those are the new dimensions of my smaller box. Okay, that's it for this section. The rest is your practice. This is your homework. And then section 6.2 is multiple transformations, so just doing more than one thing. So practice these, get good at these before you move on to section 6.2.